So, good evening, good morning, and good afternoon, ladies and gentlemen. So, today I'm very pleased to host this CIB Presidential Seminar to the audience under the umbrella of CIB. And today I would like to introduce today's speaker, Dr. Lin Wang. Dr. Wang is a research officer in the Construction Research Center at the National Research Council, Canada. His research focuses on hydrothermal performance analysis, energy efficient retrofit, and climate resilient design of building envelope systems. He holds bachelor's and master's degrees in HVAC engineering and a PhD degree in building engineering. He has extensive industrial and academic experience in energy efficiency and sustainable building design. Dr. Wang has led the development of Canadian national guideline on assessing the risks to moisture-related deterioration of building envelope systems under climate change. He initiated CIB W040 research program for 2025 to 2028 and led the development of working agenda. His current work is to advance stochastic simulation approach for probabilistic assessment of passive energy conservation measures. So now I'm very happy to hand over the screen to Dr. Wang. Dr. Wang, please.
Yeah, thank you. Thank you so much for introduction, Professor Fang. Good morning, everyone. Good evening, everyone. I'm very pleased to be here today to present some of the stories of CIB W040 and talk a little bit about our research program, passive energy conservation measures to mitigate climate change in built environment. Oops. Okay. So this is the outline of my presentation today. Firstly, I'll briefly introduce the history of W040, and thereafter I will provide an overview of our current working program. And finally, we'll talk a little bit of our ongoing tasks. So as one of the oldest working commission in CIB, W040 has witnessed the half-century development of heat and moisture transfer in buildings. So this is the objectives of W040, and there are many bullets on our websites. But in one sentence, our mission is to understand all of the heat, air, and moisture transfer phenomena in buildings, from material to building envelope system up to the whole building, and transfer the fundamental knowledge to industry. W040 was founded in 1969, the eve of energy crisis in 1970s. The energy crisis has driven the standardization of moisture profile analysis of the insulated walls, and most of the standards in that period adopted the vapor pressure gradient analysis for condensation assessment of the walls with insulation, but there was no consideration of moisture capacity and capillary activity in building materials, and no dynamic analysis. The coupled heat and moisture transfer model rooted from soil science has inspired the adoption of moisture sorption and liquid transfer in building materials, and constructed the foundation of the first hydrothermal model in 1970s. And the model was validated by hot box experiment. As you can see from the picture on the left, there were two environmental chambers to mimic the outdoor and indoor environment separately, and different wall configurations were put in the middle, and heat and moisture behavior of the wall were monitored to validate the hydrothermal model. Although today's hot box apparatus is much more advanced than that in 50 years ago, but the fundamental idea had never been changed. The 1980s saw a spring of hydrothermal model development, which constructed the ground of two international collaborative programs in 1990s, the IEA Annex 24 and 21. In Annex 24, 29 hydrothermal models were developed, and Task 1 report summarized the features of different models, but there was no whole building analysis, as the objective of this program was to investigate the well-insulated building envelope systems. And in Annex 21, 24 version of 70 whole building thermal insulation models was evaluated against the actual performance, actual measurements, but the moisture behaviors were not considered in those models. So in the decade of 2000, there were two remarkable international working programs in the area of building science, Hampstead and IEA Annex 41. In the Hampstead project, there were two tasks, and material level study and the building envelope system level study. In the material level study, a round-robin test of high-grade property of 3 materials was implemented among 6 labs, and repeatability and reproducibility errors were quantified based on test results, and the error sources was also identified. Sorry, pardon me? Okay. So the round-robin test is helpful for reaching an international consensus on the best practice of material property characterization and to improve the reliability of the measurement results. For the envelope system level study, the benchmark exercises of different wall assemblies were carried out among 8 models from eight organizations. And this benchmark exercise formed the foundation of the European standard of hydrothermal modeling. IEA Annex 41 moved to the whole building heat, air, and moisture analysis. And this project included 4 tasks: modeling exercise, experimental testing in indoor environment measurement and control, and long-term performance technology transfer. By the end of this project, the international consensus has been reached regarding the whole building harm analysis approach. It should include energy modeling, hydrothermal modeling, and airflow modeling. So what is the relation between W40 and these international collaborative projects? Actually, W40 was the primary battlefield to foster the international collaborative activities and disseminate the research outcomes. For example, W40 meeting proceedings in 2000, there were some papers regarding whole building hydrothermal analysis, hydrothermal measurement for harm model validation, and as well as the hygroscopic inertia of the indoor humidity control. And the basic ideas of these papers were adopted by the Hampstead and Annex 41 project. And these are some remarkable papers that were published in W40 conference proceedings in 2004. For example, the reliability assessment of interlab comparison of the material property measurement reported the outcomes of Hampstead project, and the sensitivity analysis of moisture response of building envelope to moisture loads is a complementary study of the Hampstead project. And CFD was introduced for wind driven rain analysis at that time and published in W40 proceedings. Although the UAV thermography is considered an emerging technology to detect hydrothermal performance of the wall, the application of infrared thermography was explored 20 years ago by W40 researchers. And climate change is not new to W40. The researchers have already investigated the impact of climate change on hydrothermal performance 20 years ago. So there were some significant international events or trends in the end of 1990s, such as the foundation of IPCC, the international initiative of a sustainable built environment and widespread of green building standard, the crisis of moisture damage of houses, as well as the advancement of hydrothermal and energy modeling tools. All these events or trends have driven simulation-based design become a common practice in construction industry. However, at that time, people used deterministic simulation with no consideration of the uncertainties of all the input parameters. Another international collaborative project, IEA Annex 55, addressed this knowledge gap. So in that project, researchers used Monte Carlo-based simulation for probabilistic assessment. The input parameters are considered as stochastic variables, which follow probability distributions, and the stochastic simulation could be performed to derive the probability distribution of the results. The stochastic simulation can generate a large amount of data, which paved the way of machine learning model development in the second half of 2010s. In the decade of 2010, W40 has compiled all the heat, air, and moisture transfer terminology in existing books, standards, and other reference documents. And W40 researcher initiated an international survey considering moisture safety in buildings during design and construction. And the survey showed that a third of construction projects during the second half of 2010 were affected by moisture problems, and most of the industrial people in Europe believe that the guidelines are more helpful than building codes. So our current working program was developed standing on the previous international collaborative research activities. The title is Probabilistic Assessment of Passive Energy Conservation Measures and a Changing Climate in an Urban Setting. Again, the stochastic simulation approach will be adopted to investigate the passive energy conservation measures for energy efficient and thermal comfort and moisture safety design. So let's move on to our working program, starting from a changing climate and GHG emission. So we all know that the global warming is largely caused by the GHG emission, and the construction sector accounts for around 40% of global GHG emission. And the table on the right shows that the current and projected future urbanization rate of some countries or regions. As we can see, for some regions such as North America, Europe, Australia, and Japan, the urbanization rate has been stabilized. But for other countries such as China, India, Africa, the urbanization rate is still expected to be increased in the next 25 years. So global warming brought a global challenge of heavier environmental loads for the industrialized countries. The primary challenge of GHG emission reduction is the deep retrofit of existing buildings. For the countries which is still in the progress of urbanization, they are facing both challenges of deep retrofit of existing buildings and improved efficiency of new constructions. The figure on the right shows the activities in the service life of a building. The working program of W40 focuses on the design stage. The goal is to use the robust probabilistic assessment approach to accelerate the decision-making process at the design stage to ensure the energy efficient and thermal comfort and moisture safety performance of the building. Before we move ahead, I would like to introduce myself a little bit. So I studied and worked in the city of Beijing from 2006 to 2013. I fortunately witnessed the rapid growth period of Chinese construction industry. After got my master's degree of HVAC engineering at Beijing University of Civil Engineering and Beijing University of Civil Engineering and Architecture, I went to the green building design industry, which was in an early booming stage at that time. So my job was to do the energy modeling for the buildings which seek for LEED certification. And it was my great fortune to participate in many projects of landmark buildings. Most of those buildings are skyscrapers. They generally have the structure of steel reinforced concrete, and building envelope systems are generally the curtain walls. They generally have a complicated HVAC system, including chillers, boilers, AHU, and terminal devices. So the way we do the modeling follows the procedure of design, including schematic design and design development and construction documents. In the phase of schematic design, we choose the templates of the building envelope and HVAC systems based on information of climate zone and type of the building. In the design development stage, we need to select the building materials, configurations, the HVAC components, piping, ducting layout to help ensure the system efficiency and indoor air quality. We run simulations again and again to study different energy conservation measures. Under each energy conservation measure, we adjust the detailed parameters until you figure out the best ECM and detailed design that provide maximized energy saving. But the energy saving is not only criteria for building design. We had a lot of design meetings with different specialists, such as architects, structural designers, facade engineers, mechanical engineers, and EE engineer landscape architects. And there were generally many rounds of iterations among different designers to come up with a feasible design with all the considerations of cost, structure and fire safety, energy efficiency, thermal comfort, and sustainability. We, as a simulation engineer, will provide feedbacks to different designers on energy performance. Sometimes we do the wind and thermal environment simulation to provide the wind and thermal performance, wind and thermal environment performance, and sometimes lighting performance to support them to make a design decision. So there were many voices to criticize the green building certification. People doubt about the real performance of the building that were awarded with LEED certification, and many studies investigated the differences between the real performance and simulated performance at the design stage. The general conclusion was the difference is large, and these differences could be contributed to many factors such as the stochastic occupant behaviors, insufficient commissioning of HVAC system, and the insulation strategy in many energy standards is not sufficiently climate adaptable. So to address the last question, I started my PhD study, stochastic modeling of hygrothermal performance of highly insulated wood frame wall in Concordia University at Canada, Montreal, Canada. So this table shows the R value requirement by National Building Code of Canada of above grade wall at different climate zones. But for high performance building that comply with green building standards, the R value are generally increased to 5 to 7. So, however, most of the energy standards do not specify how to increase R value of the wall. I have investigated two strategies to increase the insulation in the stud cavity or add on the insulation of an at the exterior wood sheathing. And such strategy also have each strategy also have multiple detailed variations, such as the type of insulations and cladding ventilations and the type of exterior water resistive barriers. And these insulation strategies may lead to a higher moisture-related deterioration risks. For the stud cavity wall, there will be higher condensation risk due to the air exfiltration. And for the exterior insulation wall, there might be a lower drying potential when the rain leakage occurred. And these risks are influenced by many factors, such as the material properties and boundary conditions. So inspired by my energy modeling experience and learned many research outcomes from Annex 55, I developed the stochastic modeling framework, which is the combination of scenario analysis and stochastic analysis. The scenarios can be different types of moisture loads. It can be the combination of different design strategies, design scenarios. For each scenario, the design parameters can be considered as stochastic variables organized by advanced sampling techniques. And stochastic simulation can be performed to derive the results for sensitivity analysis to identify the important risk factors or design parameters, as well sorry, for risk assessment to unveil the potential risk of the moisture deterioration. So by using this framework, the mold growth risks of different highly insulated walls in different climate conditions can be quantified. This information can help the designers to select proper wall configuration, insulation materials under different climate conditions to achieve the desired R value and minimize the moisture-related deterioration risks. In 2020, I brought this stochastic modeling framework to National Research Council of Canada, and I developed the framework of decision support tool for climate resilient building envelope design. So this is actually the starting point where I developed the working program of W040. In this framework, we will have the client side and server side. In client side, we can input the wall configuration, the material properties, boundary conditions, and climate conditions. And all this information can be considered as stochastic variables and pass them to the server side. In the server side, we firstly screen whether the information has been trained or not. If it's trained by the AI model, and we call the AI model directly provided output. If not, then we run the stochastic simulation and enrich the AI model. The output can be used to support code compliance evaluation and support the design. Although this framework has not been realized, but in the past years, we did a lot of work of different components in this framework. For material properties, we quantified the uncertainties in our lab measurements. Instead of using single values for simulation, we applied stochastic simulation to pass these uncertainties into the simulation results. We also developed a method of using machine learning model to estimate the property values that were missed in our database based on other measured properties. The researchers from United States, Germany, Belgium, and Netherlands also did similar studies in the past years. For example, the researchers from United States and Germany applied regression analysis to estimate the moisture content at different capillary pressure based on limited measurement. The researchers from Belgium and Netherlands discovered the relationship among different basic material properties of brick, so that people can estimate one property based on other properties with a different level of confidence. For thermal-related boundary conditions, we have investigated the temperature of exterior surface of walls exposed to different local landscape elements. For example, these thermal images were taken in the morning of a heat wave day for office building at Ottawa. For the east facade, which perpendicular to the rays of the sun, the temperature difference between surface with and without shading can be up to 20 degrees C, while for the south orientation, the difference is around 10 degrees C. Other factors such as absorptivity and emissivity of the building surface also significantly influence the surface temperature, and these properties can vary with environmental conditions. The wind-driven rain is one of the most important moisture sources that influence the building envelope performance. In the past decade, Researchers from Concordia University did a lot of experimental work to characterize the catch ratio at different locations of the building. That is the proportion of the rain reached onto the surface of the wall to the horizontal wall. We can see from figure on the left, there is a large variation of the catch ratio at different locations of the building. And Belgium researchers also compared the amount of wind-driven rain from field measurement with that calculated from empirical equation in ISO and ASHRAE standard. The large discrepancies were found between the measured and wind-driven rain and calculated wind-driven rain. And the wind-driven rain can penetrate into the wall through unexpected deficiencies. The amount of the rain penetration is related to the wind pressure and intensity of the wind-driven rain. In the past few years, the researchers from Gand University of Belgium and my colleague at NRC did a lot of experimental work to quantify the amount of wind-driven rain for different wall configurations and different environmental conditions. The air movement around the building envelope systems will also influence the wall performance, such as the cladding ventilation rate, the air exfiltration, and the air movement are influenced by the wind pressure, buoyancy pressure, and the air tightness conditions of the wall. So all the boundary conditions mentioned above, all the boundary conditions mentioned above are influenced by the climate conditions, which is always change in the short-term or long-term period and micro or meso scale spatial locations. The climate parameters at different global warming scenarios can be projected through GCM or ICM model, generally at the climatological period of 31 years. This is area of climate science. We, as a researcher of heat and moisture transfer in buildings, we generally interested in how does the global warming influence the building performance and how pick up a representative set of climate data for building performance assessment. This is an example how did we pick up the representative years in a 31-year period to capture the long-term mold growth performance of wood frame wall. We firstly calculate the moisture index for each year over 31 years. By the way, the moisture index is used to describe the moisture severity of a year. And we divide the cumulative distribution of moisture index into different intervals to compose a reference year, to compose a series of reference years, and use the reference years to do the simulation. As we can see from the figure on the right, the 7-year reference year simulations are very similar with the 31-year simulation. In this way, we can reduce the computational cost to investigate the long-term performance of the wall. We extended this study to different global warming scenarios and ran 31-year simulation at different global warming scenarios, and we used the results to train a machine learning model. Then we used the machine learning model to predict the mold growth performance. As you can see from the figure on the right, the blue boxes predicted by the machine learning model are very similar with the orange boxes predicted from the numerical model. So by using the machine learning model, we can significantly accelerate the decision-making process. And the running time for the machine learning model is just a few seconds as compared to the tons of hours of the conventional numerical model. Also, it provides a robust probabilistic assessment under different climate change scenarios. We also investigated the impact of spatial variation of climate conditions on the mold growth performance using simulations. The figure on the left shows the 4 locations in Vancouver area, and these 4 locations have different urban features, although they are considered at the same climate zone. But the first one is a small island surrounded by the sea, and the second one is in the airport, and the third one is in large forest area, and the last one is in downtown area. As we can see from the figure on the bottom right, the mode growth index in the downtown area is much lower than other three locations because it has much lower precipitation than other three locations. We further investigated the spatial variation of climate parameters in micro scale through field measurement. In summer 2024, we measured the microclimate parameters at our NIC Ottawa campus at different locations. The large lawn area, the parking lot, small park under the tree, and forest area. We use these parameters together with the parameters from Ottawa Airport to train AI model. And we use the AI model to predict the microclimate parameters. The AI model is good for some of the parameters like temperature or relative humidity, but still not very strong to predict solar radiation and wind speed. For the reference year selection study, the researchers from Belgium, from Gandhi University at Belgium, Aalborg University at Denmark, and Tallinn University Technology at Estonia, and Tsinghua University in China, they also did a lot of work to incorporate the uncertainties for long-term probabilistic assessment. For machine learning model development and spatial temporal assessment, the researchers from London University and Sweden and UCL from United Kingdom, KU Leuven at Belgium, and Arkwright National Lab at USA also did a lot of work on the AI model development and the spatial and temporal assessment of the building performance. So let's zoom out from technical details to see how could this framework to mitigate the climate change or decarbonize the built environment. Firstly, it can generate large, high quality and quantity of data for AI model development to accelerate the decision-making process for design and retrofit. It can provide robust probabilistic assessment with considering uncertainties and extreme events. The performance to be assessed can be extended to not only the moisture safety, but it can be extended to energy efficiency and thermal comfort. Let's zoom out a little bit more. So why passive energy conservation measures? So when we have a limited budget, should we prioritize additional insulation or upgrade HVAC system? My apology, I don't have answer right now. I'm a building envelope researcher, but I was also HVAC engineer. I don't want to advocate one strategy while play down another. I just want to provide some angles that we could look at to think about this problem. The life cycle cost, initial and operational and demolishing, and climate conditions. For example, in cold climate zone, the heat pump efficiency is very low, and hot climate zone, additional insulation may worsen the indoor overheating risk. And also, we need to consider building conditions. For example, many heritage buildings are difficult to install HVAC system. And finally, energy structure. As you can see from this table, the electricity consumption intensity varies a lot among different provinces at Canada, depending on the energy source. So for the cities with different energy sources, should we consider prioritize operational energy carbon or embodied carbon? So I think all this problem is not easy to be answered with one or two journal papers. I hope in the coming years there will be more PhD theses to look into this area and provide more systematic answers. So let's have a look of our ongoing tasks. So these are our ongoing tasks. These are the tasks that are planned from 2025 to 2028. In 2025, we had a systematic review of the probabilistic assessment of passive energy conservation measures. In 2026, we will have a database for hydrothermal properties of bio-based insulations and mass timber materials, because those materials are all low carbon materials. And in 2027, we'll have multi-criteria performance assessment of the bio-based insulation walls and mass timber constructions, including energy efficiency, moisture safety, and thermal comfort. So from April 2025, we started a systematic review of passive energy conservation measures. The objective of this review is to review the benefits and drawbacks of different measures, the risk factors, uncertainties that may impact their effectiveness, and the suitability of use these measures in different climate zones, and the tools and probabilistic approach for the risk assessment. So this is an overview of some of the review sections of the some sections of the report, and they included add-on insulation and moisture load, and passive cooling and UHI, and harm tools, and probabilistic assessment and reference year selection. So this report will be, we hope we can have it published in the coming month. We have also started a task, a database for hydrothermal properties of bio-based insulations. The objectives are to create a large dataset for hydrothermal properties of bio-based insulations for hydrothermal simulations, and either deterministic or probabilistic. We want to develop the data-driven approach to properly estimate the full dataset of hydrothermal properties based on the limited measurement. The dataset will be created based on literature review and lab measurements. We will use the data mining and AI approach to discover the relationship among different parameters. We have already published an extended abstract in the conference ICMB 25, and to introduce general idea of these tasks. From August 2024 until today, the researchers from 35 organizations over 20 countries have been involved in W40 activities. I'd like to thank all the researchers who have contributed or provided support of our tasks or event organizations. Finally, I would like to talk a little bit of my long-term vision of the research area of heat and moisture transfer in buildings. So numerical error is stepping down from the stage of history, and an AI era is stepping onto the stage. So no matter we are in the numerical era or AI era, the building science and data science are the fundamentals that will never fade away. The quantity and quality of the data from real world are the cornerstones to calibrate or train the models, either numerical or AI. So the meaning of this transition from numerical to AI era is to accelerate the retrofit or design, provide robust assessment for pre and post retrofit or design, and help ensure the design is properly implemented, realize the energy efficient, thermal comfort, and sustainable built environment. The historical point where we are standing on is very similar to late 1980s, the germination stage of numerical models. Although there are some AI models available in literature, the amount of the AI models and tools is still insufficient to boost an industrialization process. The data available in literature is not properly organized to boost its power for knowledge transfer, and there is still a lack of real-world data from the field measurement. So my vision is, as an international working commission, we should be together to embrace the opportunity and challenge of the transition between the numerical and AI era. We should be involved in the development of AI version of existing numerical tools, and we should initiate more large-scale field measurement to produce more real-world data. And also, we are in a race with climate change. The progress of climate change is faster than efforts that we made to mitigate the climate change. So we should adopt the emerging technology such as UAV thermography, beam integration, 3D printing, prefab modular construction to accelerate the building design and retrofit. So the NRC research activities introduced in this presentation were financially supported by the Building Envelope and the Material Resource Unit and Climate Resilient Built Environment Program at Construction Research Center, National Research Council, Canada. And I'm a nerd of STEAM, but thanks to the AI era, I can use the AI tool to generate many image to visualize some of my thoughts and the stories in my mind. Thank you for everyone.
All right, thank you, Dr. Wang, for your wonderful presentation. You brought us back to the start of the journey of W040 from 1960s, and then up to the current work you've been doing, and you also showed us a long-term vision of where this area goes in the future. So it's a wonderful presentation. We still have some time, so I'm calling for questions from the audience. Please. Questions? Any questions? Please raise your hand on the screen so that I can hand over the microphone to you. Okay, I think maybe the audience are not prepared for questions. So if there's no questions, may I suggest we give Dr. Wang a big applause for his wonderful work and
Thank
his
you.
contribution to W040 and his wonderful presentation. Thank you,
Thanks.
Dr. Wang.
Thank you, Professor Fang. Thank you, everyone.
So since there's no questions, so I would announce the end of this seminar. And if you have more questions, you can reach out to Dr. Wang in many ways. You can find his email in the CIB website. Okay, Dr. Wang, thank you so much. And now let's close the seminar for this evening.
Thank you.
Dong, do you have anything to say?
No, that's great. Thank you. Very good, and very good to see the type of work that I personally started my career in the mid 80s, still going strong, albeit into a whole new era. That's congratulations. Yeah.
Yeah, I think the W040's story could be one of the best in the CIB history.
Yes, it's very good.
Thank you so much.
Compelling.
Thanks.
Thank you, everyone. Thank you.
Thank you, and
Thank you, everyone.
goodbye, all our participants. Thank you.